I did not.
Yeah, it was quite a
Yeah. Oh, I
such a.
yesterday was fine. I know. I think that'd be good. We're not like, for something making all of the letters, it's always giving up after certain days. So it's like that place, you know. It's to be fair, whether they're not saying that these things that these are of this and those, well, we know what there's the game for these and like it's I'm not really done with because yeah, we do it's like fact meetings, it's like for me to feel like on my facilities, so after my games, we're signed up for the exam, but not
I still yesterday very fun.
Yes, I don't know if I'm not like respectful for them, like
So I'm going to do something a little bit out of order here. If you guys can turn to page 63 in packet 6. These are like multiple choice questions that may show up. These are called verify solutions problems. These aren't difficult. I think I just want us to make sure that that we know how to move through these types of problems. So whenever it says verify solutions for differential equations, all you're doing is you're gathering your derivative and second derivative from the function and then plugging in and see which works. You're trying to find an equation that will satisfy the differential equation. Or you're trying to find a derivative equation that will be a true statement, basically. So if we look at, again, page 63, the function e to the 3x minus 5x plus 7 is a solution to which of the following differential equations. You have that there's all these references to y prime and y double prime. So let's do this. Let's find y prime and y double prime, and then we'll plug into each of them and then see which one is going to be a true statement. And only one of them will stand out as a true statement. Okay, so. Okay, so all your answer choices involve some reference to y prime or y double prime. So let's just go ahead and find y prime and y double prime. So y prime is equal to e to the u's derivative is e to the u times u prime. And then 5x becomes 5. And then if I want to find y double prime, e to the u becomes e to the u times u prime. So another 3 pops up. So e to the 3x times 9 minus 5. Okay, so here's my cleaned up version. Oh, I'm sorry. Y double prime, that 5 goes away, right? So that 5 goes away. We're just left with 9e to the 3x. Okay, so now I'm just going to test each of them to see which one will remain a true statement. So y double prime minus 3 times y prime minus 15 is equal to 0. So we're just going to multiply this through. I think this will work. 9e to the 3x minus 9e to the 3x plus 15 minus 15 equals 0. Great, that works. The other one is not going to work if I plug replace y double prime with 9e to the 3x, replace y prime with 3e to 3x minus 5. I'll get plus 15, which will end up not being equal to 0. And then C and D are also not enough. We need something to counterbalance that different coefficients here, so that 3 is doing it. So answer choice is going to be just A. Okay. So all we're doing is we're just gathering y prime and y double prime, plugging it into our options and see which one is true. Let me skip to number 4 on page 65. Okay, for what value of k will y equals k sine of 5x plus 2 cosine 4x be a solution to the differential equation? So let's go ahead and get to what they're asking for. They're requiring information about y double prime. So let's make our way down to y double prime. So remember, treat k like you would a coefficient. It's just some number like a 2 or 3. But that k is going to stay because it's attached to a function. And the sine of u becomes cosine of u times u prime. And then cosine of u becomes negative sine of u times u prime. Let me clean this up, and then we can make our way down to y double prime. Okay, y double prime. Cosine becomes negative sine. Another 5 shows up. Sine becomes cosine. Another 4 shows up. So we can replace y double prime with what we found here. replace y with our original equation, and then we're just trying to solve for k. So now we're just plugging in back into our differential equation. So I'm back to the original equation here. So I'm just going to make a couple of substitutions. I'll replace y double prime with all this. And then replace y with my original equation. And then we should be able to try to figure out what k is. Okay, so again, we're on page 65 here near the end, just going over these specific types of problems here. Some things will cancel out nicely. So I see the cosine 4x's, 32 cosine 4x's will go away. A bunch of like terms here. What if I left the 16k over here and then just added that 25 sine of 5x to the other side? Let's see, 25k. Oh, sorry, negative 25k. Sorry, I messed up. The k is the coefficient. It hangs out for the entirety of the problem. So y prime, I dropped the k here, but the k is still going to remain. So actually, these are like terms. So I get negative 9k. Divide both sides by negative 9 sine of 5x. Get k by itself. And the only thing left is negative 27 over negative 9, which is a 3. Okay, let's try number 5. You have all these mentions of y double prime and y prime. So we're going to find each of the derivatives for each of the functions, plug it back in, and see if any of them will produce a true statement. Okay, first option. So I'm going to find y prime, y double prime, insert them into my differential equation and see if it will be a true statement. If it is, I'm going to keep that as a solution. Then I'll try the second. I'll try the third one as well. Cosine of u becomes negative sine of u times u prime. So another 3 will pop up. Multiply with that 6, I get negative 18. So I'm going to put all this into my equation to see if it's a true statement or not. If it's true, I'm going to keep it. If not, then I'm not going to indicate that as a solution. So y double prime first. Minus 10 times y prime plus 9 times y equals 0. Is that a true statement here? So negative 18 sine plus 18 sine, that's fine. That goes away. But we're still left with this positive 60 cosine 3x. That's not canceling out, and that's obviously not equal to 0. So this is not a solution. Doesn't end up canceling out to be 0. Okay, second option, y equals 5e to the x. Let's find y prime and y double prime. All my derivatives will remain the same. Now I'm going to put it all into my differential equation. Minus 10 plus 9 times e. Let's see if that's equaling out to be 0. So 5 minus 50 is negative 45 e to the x, negative 45 e to the x plus 45 e to the x. Yes, that's true, right? All this cancels out to be 0. This is a solution. We'll keep 2 as a solution. Okay, option 3, y equals ce to the 9x. We don't know what c is, so we'll just leave it as some unknown constant. Okay, y prime will be 9c e to the 9x. Y double prime would be bring down another e to the u becomes e to the u times u prime. Another 9 will show up, so 81c e to the 9x. Take all this information, put it into my differential equation. Minus 10 times this. plus 9 times CE to the 9x equals 0. So 81 minus 90 is -9, and -9 plus 9 is 0. So this does work as well. So option choice D. Okay, so that's the case for a lot of these problems near the end of the packet. It's just solving these confirming a differential equation. So you're just going to gather whatever data they're looking for and then plug in and see if you're either solving for a missing unknown k or you're just verifying whether that solution stands. I do want to take time to go over two specific things I noticed as I was grading your FRQs and your multiple choice test. Just two things stood out. One was just problems involving like, when do we find slope? When do we take the area? When do we use first theorem? And I feel like on the as I was grading, it feels like some of us were getting things mixed up or thinking that one was a process for the other. And then also, I just want to do a quick review over area and volume, especially volume, like cross-section, volume with cross-section versus this method or washer method. I think some of us may have forgotten a little bit about cross-section, and we just assume everything is this method or washer method. And I saw that to be a common theme. So just created another worksheet here just to address some of those issues. Okay, so going back to FRQs briefly here. Okay, water is flowing into a tank over a 12-hour period. The rate at which water flows into the tank at various times is measured, and the result is given in the table below, where RT is a differential function, so we know it's a smooth curve. It measures gallons per hour. The tank contains 150 gallons of water when t equals 0. Okay. Part A, use the table to estimate the value of R prime of 6. So R prime of 6 is basically asking for the derivative of r at 6, and we don't have a function to find the derivative. So the next best thing is approximation using slope, right? Because we know slope and derivative are related. Slope is just the approximation version of derivative. So we can just pick the two closest points between close to 6 is 5 and 7. So we're just basically going to find the slope there. So change in r of t over the change in time. So 9. So we always do change in y over change in x. Think of r of t as your y. Think of t as your x. Plug that in the calculator. I get 0.2 divided by 2, which is 0.1. And then our units, we're finding a rate of change. So this gallons per hour is going to turn to gallons per hour squared. So what does that mean? So this tells us that my rate, if you look at your rate here, 8 to 8.8 to 9 to 9.3, for the most part, my rate is increasing, right? And that's what this r prime is telling us. R prime is telling us that at this point, my rate is increasing. So we want to use those words, that the rate at which water is flowing into the tank is increasing by 0.1 gallons per hour at t equals 6 hours. The units is gallons per hour squared, but we can also say increasing by this rate, right? So if we say increasing by this rate, that's also meaning the same thing as gallons per hour squared. But the key words here is looking, understanding. We got to include this that idea that the rate is increasing because we're talking about something at the second derivative level. Part B, estimate the depth integral using two trapezoids. So trapezoid, that's great. We can, they're telling us what to use. So we do, remember your trapezoid formula is 1/2 width, height 1 plus height 2. And then we just set up our intervals from 0 to 7. That will be one trapezoid. From 7 to 12, that's another trapezoid. If I subtract the width, that will give me the, subtract the times, that'll give me the width. And then I'm just picking out the heights at the ends here. So my first trapezoid, I'll use 8 plus 9. Second trapezoid, I'll use 9 plus 9.2. And then if we're taking the antiderivative, your units will change, but the rate will turn into something above it, right? So gallons per hour is no longer gallons per hour. This is now going to be in terms of gallons, right? We're accumulating these gallons per hour over time. We're going to now be sitting at gallons. Some students have just a little bit of trouble with trapezoids, so make sure that we remember it is not, there's a 1/2 in front, and it's not just width times height. And also the height we're adding together, we're not subtracting. Some students were subtracting, maybe because you're subtracting for the width. And then students also decide that they want to subtract for the heights as well. You're going to add the heights, but you are going to subtract your intervals to get to your width. So what does this tell us? This tells us that over this 12-hour period, after we accumulated all this rates, we're going to actually find out how much water has entered into the tank. So 105 gallons, that's the estimated amount of water that's entered into the tank over this 12-hour period. Part C, use the data in the table to estimate the depth integral from 0 to 12 of r prime of t dt, then use correct units to interpret the meaning in the context. Now, I purposely put these next to each other because they look so similar, right? They look like, well, can I just do the same thing? But I can't because this is actually asking for the area under the r of t. This one, you could think of adding the area under the R prime, but we don't have the R prime table in front of us. So we got to use a different method. We got to figure out, how can I get this into something that I can use? How can I get that R prime in terms of R of t? So we have a different process for this, right? This one, we can actually just figure out, well, what can I do with the integral? Can I actually evaluate this integral? And what's available to us is first theorem, right? First theorem, we can take the antiderivative of R prime. R prime will rise up to in terms of R. And so this will allow us to take advantage of what we're dealing with. Now, if the table was R prime, then great. We can use trapezoid or rectangles or whatever approximation or whatever area they're asking us to use. But we don't have R prime in front of us, but we can convert that into R of t by using first theorem. So, a lot of times these three concepts are back to back to back. And I just want to just make you aware. Sometimes you're finding area, sometimes you're finding slope, sometimes you're using first theorem to get it into something that you can use. And that's what we're going to do here. So R prime can turn into big R, or R of t. So if we do first theorem, R prime is just R of 12 minus R of 0 after we plug in upper and lower bound. And this we can do, right? Because we have R of 12, we have R of 0. So we have 9.8 minus 8, and that still gives us gallons per hour. So what does this tell us? What does this tell us about what's happening? Well, we know that the rate was 8, and it goes up to 9.2. So therefore, over this 12-hour period, my rate has increased by 1.2. So over this 12-hour period, the rate of water flow has increased by 1.2 gallons per hour. It's like turning on the water in the faucet, and you're just continually increasing that dial. As you continue to increase that dial, more and more, your rate is increasing. So in a sense, between 0 and 12, how much have you increased? How much has your rate increased? Your rate has increased by 1.2. Part D, is there a time or is there a value where R prime is equal to 1/7? Again, if they're asking for a specific value, there's two options here, and it's either IVT or mean value theorem. IVT is always the one that we prefer to try, but if you look, we don't have R prime to actually look for values, right? We don't have R prime to look at these values, and we can't say, oh, I don't see 1.2, I don't see 1/7 here, so therefore that's not the case. We don't have a data at this level, but we know that R prime is the derivative or the slope of R of t. So if we're looking for something at the slope level or at the derivative level, we're going to rely on mean value theorem. So we're looking for two order pairs that will give us 1/7. And if we scan across here, all these are decimals, these are messier. What about between these 2 points, right? 9 minus 8 is 1, 7 minus 0 is 7, we get 1/7. We get a slope of 1/7. If there's a slope of 1/7 at the R of t level, we know R prime is also going to experience that 1/7 somewhere. So that's mean value theorem. Since R of t is differentiable and therefore continuous, and we're showing that there is a slope of 1/7, we can guarantee there must be an R prime equals 1/7 as well on that interval. Part E, estimate 1/12 of the depth integral from 0 to 12 of R t using two trapezoids. If you look at part E versus part B, they're very similar. We're both using trapezoids for B and E. The only difference is that there's a 1/12 in front. So what that's doing is, after we find this integral of R of t, we're going to get that 105 just like before, because the same process, same interval, but then we're dividing by 12. So that means we're back to gallons per hour. 105 gallons over a 12-hour period, and then because we're back to gallons per hour, we have to recognize that, oh, if there's a fractional coefficient in front of my integral, a lot of times it's trying to get us to use, trying to identify with average value theorem. So here, the number we get is going to be the average rate of flow of water entering the tank in the 12-hour period, which is 8.75 gallons per hour. And this should make sense because if you look at all your data here, 8, 8.9, 9, 9.3, 9.2. If I were to ask you to give me a ballpark average of all these numbers, you'll probably say something in that upper 8 or lower 9 region, right? Somewhere between 8.8 and 9 is the average between all these numbers. And that should make sense as well. 8.75, that is consistent with what we can estimate just from our table. So this tells us, again, average rate of flow of water entering the tank in the 12-hour period is 8.75 gallons per hour. Back page, I put a lot of the area and volume processes next to each other so that we can distinguish between them, and that we can just do one final practice with area and volume. So after you're done, let's go to page 2. I'm going to stay on this page for another second, but if you guys can go to page 2 once you're ready, look at your diagram here. It's all the same diagram, but part A is asking for area, part B is cross-section, part C is rotation around an axis or around a vertical or horizontal line. So area, how to do area? Well, we always want to try top minus bottom first, right? That should be our default. If that fails for some reason, then we can look at right minus left. But you usually, don't put them at the same level. Just always assume top minus bottom. And if your equation is strange, if everything is defined a different variable, then maybe you can explore right minus left. But so for part A, identify your top graph, identify your bottom graph. Top minus bottom. Number 2, remember your area formula is this. That's it, right? Just the integral of top minus bottom. There's no square, there's no pi. It should look simpler than the volume formulas because we're not going to the third dimension. We're just dealing with a second dimension here. So the furthest left we see is 0. The furthest right, x value you see is 9. The top graph is that horizontal line, y equals 6. The bottom is that square root, radical, 2 root x. And this is non-calculator, so we want to go through our full process. So power rule, plug in upper and lower bounds, and then get down to your decimal answer, or get down to your solution. And for part A, you should get 18 as your area. 6 becomes 6x. 2 root x, the same thing as 2x to the 1/2. We go through power rule for that. Add 1 to the exponent divided by the new exponent. Clean up that fraction, plug in your upper and lower bound. You could leave your answer in any of these stages. But I think it's good to practice getting it all the way down to a numeric answer. Because if it's multiple choice, we have to get it all the way down to this to match our answer choice, right? So I just want to point out, if it feels like it's difficult to do 9 to the 3/2 by hand, then keep reminding yourself that you don't have to do the 3 first, right? 9 cubed, that's a difficult process to multiply that number out, and then take the square root of that. Will take some time. Much easier is do the square root first, right? Square root of 9 is 3. And then once I get that down to 3, then 3 cubed is a lot easier, which is 27. So okay, part B, we have a region that's a base of a solid, cross-section taken perpendicular to the x-axis are squares. So I think a lot of students were thinking, a lot of students forgot about cross-section on the multiple choice test, and they started doing rotation around just making it into a disc or washer method. But cross-section is different. Cross-section, you're building your base length much the same way as area. Okay? You're doing, but also with area, I would say default is top minus bottom, right? Sometimes it could be right minus left, but you have to make that decision. For cross section, they're going to tell you which way to draw that base length. You're not going to have to guess. So they're telling you perpendicular to the x-axis. So x-axis is this way. Perpendicular, we got to make it vertical. So that's one thing. Okay, this is more clear with cross sections than area. Area, you have some potential room for different methods, but cross section, there's no they're going to tell you explicitly how to draw, which orientation to draw that base. So now we draw that base. So 6 minus 2 root x, just like how you find initially how you found area with top minus bottom. But then after we get that 6 minus 2 root x, we're now moving on to our area component, right? And we want to build squares out of it. So squares is a certain formula there, right? Base squared. There's equilateral triangle, there's semicircle, there's isosceles triangle with leg on the base. They all have base squared, but just with a different coefficient. Squares are the easiest. It's just base squared. So we take our base length, put it into our base squared, and then we have our area formula. So you've gone through the most difficult part of the process, because now to get from that second to third dimension, you just put an integral around it, and then your bounds is the same as in terms of x, right? And there's no pi in front. It is just that base squared. And part B is only asking for you to set it up. But technically, this is manageable enough to work it out by hand. You just FOIL everything out, expand everything out, do power rule, and plug in upper and lower bound. Now, part C, write but do not evaluate an integral expression where our region R is rotated about the x-axis. Only if you see the word rotation are you going to be dealing with disc or washer method. Okay? Otherwise, if it's volume with cross-section, there's no rotation. You're just building your base length. So in this case, this is going to be washer method, because if we look at our dotted line, there's an obvious gap between the dotted line and the axis and the shaded region. So we extend our big radius from our axis to the furthest region, furthest boundary, and then little radius from our axis to the closer boundary, top minus bottom for both. And then our formula is big radius squared minus little radius squared. Part D, we are rotating around the line x equals -1. So this is now a vertical line. And then our radius has to come out horizontally. And because your radius comes out horizontally, you have to rewrite your equation. This is forcing you to get your equation in terms of y. So I got to solve for x here. This is x equals 0. This is x equals -1. We do right minus left. But it's still going to be washer method because we still have a gap between our shaded region and our axis of revolution. So we can't let this curve stay as y equals 2 root x. We have to solve for x. So divide by 2, square both sides. We want to call this curve a different name, y squared over 4. This vertical line is x equals 0, and then our axis of revolution is x equals -1. Everything we're using is going to have that equation that starts off as x equals. And we do right minus left for my big R, right minus left for my little r, and then just put it into my Walker method formula. Notice that you are using your y variable as your integrand. So your bounds need to be your y values as well. Now I want my lowest and highest y values represented of the shaded region. So from 0 to 6. Okay, real quickly here. I know some of you guys may not be here tomorrow. Maybe you have some additional AP exams you got to take. I have some additional handouts. This is not by no means required. It's not homework. It's not for a grade. But I have a full 2016 AP exam, the international version from 2016. It has FRQ, multiple choice, and solution key. So if you want a full practice test, that's there to pick up. I also have the 2024 FRQ. Notice your packet 5 only goes up to 2023. I saved the 2024 where you guys, if you want to do it over the weekend, you can pick that up. And then also, AP Classroom has 3 years worth of more recent multiple choice tests. So if you want to get that practice in, you can do that. Tomorrow morning help session, but then I also want to do a help session on Sunday night on Teams. So 8:30 to 10, I'll go over the 2024 AB FRQ. You can work through each of the problems if you find that helpful before your exam you can join for that. And I'll send out a Zoom link Sunday night if you want to join. Okay, all right, go get your phones.
Yeah.
Can I go ahead and turn? Yeah, let me just check it and I'll be right here. Yeah.
Well, I mean, yeah, it's so general. Skinny folks. Yeah. Last year.
I got to check it out. Thank you.
You know it.